Bismillahirrahmanirrahim. Assalamu alaikum dear students. I hope you all are fine and in the best conditions of your health. So today, for the course of organic reaction mechanism, today we shall discuss about a brief overview of mechanisms in organic chemistry. Key concepts which we will discuss in this lecture are the reaction mechanism, energy profile diagram, the transition state, reaction intermediates, and then we shall study about briefly kinetic stability and thermodynamic stability, and then we shall discuss about the different type of organic reaction mechanisms, which basically include the polar reactions, the free radical reactions, and the pericyclic reactions, right? So firstly, organic reactions mechanism. So in the previous lectures you have studied about different type of organic reactions, which include the addition reaction, substitution reaction, elimination reactions, and rearrangement reactions, right? And you also studied about the different types of each type of reactions. But what do we mean by the term reaction mechanism, right? So reaction mechanism is basically a description of how a reaction takes place, right? How we can convert the reactants into products. So it's not just a simple arrow that when you write then reactant get into products. So there is a whole sequence of events, and this sequence of events through which a reactant is converted into product, the sequence of event is called the reaction mechanism. And this sequence of events is indicated by means of arrow, right? So whenever your teacher says that you have to draw a reaction mechanism, you always understand that you have to draw the curved arrow, right? So what do these curved arrow means? The curved arrows are used to indicate the movement of two electrons, right? So whenever you are using a curved arrow which has a full head, means it has head like that one, then the curved arrow indicates the movement of two electrons, right? And these electrons are showing where the bonds are actually broken and which part the bonds are actually formed, right? So here in this example you can see here that hydroxide ion, this negatively charged ion, is attacking on a hydrogen, right? So this is the curved arrow, and what it's showing, it's showing the direction of motion of electrons. So always remember that the arrow always points from the electron rich to electron deficient center, right? So here this is indicating that there is no bond between them previously, but the curved arrow is showing that we will get a bond between this oxygen and hydrogen, right? So whenever you see two or more curved arrows in a same figure, like this one here, then it means that the movement of electrons are occurring simultaneously, right? So here this hydroxide ion is attacking this hydrogen, and at the same time this chlorine is leaving with this electron pair. You can see here that this electron, the direction of this arrow is from the bond to chlorine. It means this bond is being broken and the electrons are shifting on the chloride ion. So we'll get a chloride ion here by the breakage of this bond, and we are forming a bond between oxygen and hydrogen, right? So in this way the mechanism indicates you that where is the point of actual bond formation and which is the point of actual bond breakage, right? And whenever you see the two arrows or more than two arrows like this one, it means that movement of electrons is taking place simultaneously. So the attack of hydroxide ion on the hydrogen and the leaving of chloride ion, these steps are taking place, both of these steps are taking place in one single step, right? They are occurring at the same time, they are simultaneous, right? So here we have our two products, our two reactants, A and B. So one is the hydroxide ion and another is the HCl, right? And what we get is that we get a water and a chloride ion. So this is the product, this is a reactant. But the reactants do not convert directly into product. Reactants have to get through a transition state. What's the transition state? Transition state is an imaginary state in which the bonds are being formed and the bonds are being broken, right? So here in this case, the oxygen and hydrogen, so oxygen is approaching hydrogen and the bond is being formed, right? The bond has not formed yet, but the bond is forming. And here between H and Cl, the bond is being breaking between hydrogen and chloride. So the bond has not completely broken, it is in the process of breaking, right? So whenever you see a transition state, you'll always see a symbol like that one. So this symbol is indicating a transition state. So whenever you see this symbol, that line which is being double crossed, this is indicating a transition state. So it's a transition state. Transition state is actually an imaginary state in which the bonds are being broken and the bonds are being formed, right? So bond has not actually broken completely and the bonds have not been formed completely. So this is an imaginary state which is showing some intermediate stage between a reactant and a product, right? So just remember the transition state is an imaginary state, right? So the reaction mechanism, which is actually the sequence of events, which take place when a reactant is being converted into product. So the reaction mechanisms indicates where is the electrophile, what's the role of electrophile, what is the role of nucleophile, and whether there is some leaving group present or not, right? So it's an electrophile. Electrophile is electronically deficient attacking species, right? And a nucleophile is electronically rich attacking species, right? So we say that electrophile is electron deficient attacking species, but actually electrophile is not attacking itself. Electrophile is always a species which is being attacked, right? So electrophile is a species on which something attacks. Electrophile cannot itself attack, right? So electrophile is electron deficient, and whenever there's electrophile, means that that's electron deficient, something which is electronically rich will attack on it, right? So by definition we say that electronically deficient attacking species is called electrophile, but actually electrophile is not attacking, it is something which is being attacked on, right? So the presence of leaving group is also indicated by the reaction mechanism. For example, just see this reaction, right? Again we have hydroxide ion, and this hydroxide ion is attacking on the carbon, right? You can see hydroxide ion is having negative charge, right? So it means electronically rich. The electronically rich attacking group is called a nucleophile there. So in this specific example, the hydroxide is a nucleophile and the hydroxide is attacking on a carbon which is electronically deficient, right? So the electronically deficient center on which the nucleophile is attacking, so this center is called an electrophile. And here the chloride ion is leaving. You can see here the bond is being broken, right? So the bond is indicating the presence of two electrons, and this bond is broken so that the two electrons are going towards chloride, right? So chloride is leaving with two electrons. So when a leaving group leaves with its electron pair, such a leaving group is called a nucleophile. So the chloride here that's leaving is leaving with its electron pair, so that's why chloride is called a nucleophile. But if a leaving group leaves without its electron pair, right, for example a proton, right, so whenever proton leaves without electron pairs, right, so proton always leaves in the form of H positive ion. So whenever you see a leaving group leaving without electrons, then such a leaving group is called electrophile, right? So whenever you see hydrogen leaving in the form of H positive ion, you should know that this is called an electrophile, right? You should know about these terms: electrophile, nucleophile, electrophile, and nucleophile. Right, so the reaction mechanism does not only indicate about the movement of electrons that occur during bond formation, but it also indicates the order in which bond breakage and bond forming occurs, right? So some reactions they involve bond formation and bond breakage simultaneously, right? So bond is being broken and bond is formed at the same time. But some other reactions they involve firstly the bond breakage and then bond forming. Right, so the reaction mechanism also indicates what's the order of bond breakage and what's the order of bond formation. For example, let's consider this example. So here we have tertiary carbocation, we have tertiary alkyl halide, and the first step you can see that chloride ion is leaving. So chloride is leaving as a nucleophile, and what we get a carbocation here, right? So firstly, what happens that the bond between carbon and chlorine is breaking, and we are getting a carbocation. And the next step, this anion, this is attacking on this carbocation, right? So in the first step we broke the bond, and the next step the bond is forming to form the product, right? So this is an example in which the reaction is occurring in two steps. Firstly we are getting a carbocation, and in the next step we are getting the attack of the nucleophile on the carbocation that was being formed. Let's consider this example again, right? So these reaction mechanisms involve two steps, right? The first step, the leaving group is leaving in the form of a nucleophile, right? And the next step, the acetate ion, this is the acetate ion, it's attacking the nucleophile, right? So here the carbocation is being formed is highly reactive, right? So this is highly reactive and it cannot remain like this forever. What happens that as soon as this carbocation is formed, it will quickly react with any nucleophile. Right, so this carbocation is actually formed. It's not imaginary species, that's a real species. But the thing is that this carbocation, which is real, is highly reactive and cannot exist for much longer. So as soon as it's formed, the nucleophile attacks on this carbocation and we get the formed product. Right, so this carbocation which is being formed in the reaction, this is called the reactive reaction intermediate. Right, because it is formed as an intermediate step. Right, so the reactant cannot get converted into the product unless this reactant is firstly converted into a carbocation. Right, so carbocation is something intermediate in a step, so that's why it's called reaction intermediate. Right, so far we have discussed about the nucleophile, electrophile, electrofuge. We have also studied about the transition state, which is an imaginary state in which bonds are being formed and broken. And then we have studied about the reaction intermediate. Let's consider about an energy profile diagram. So normally when reactions are involving a neutral molecule, right, you're not considering some ionic compound, you're considering an equivalent compound. So whenever covalent compound has to react, it cannot react until it has certain amount of energy. Right, so neutral molecule cannot react until it has certain minimum amount of energy, and this amount of energy is needed to stretch the bond, bend the bond, or distort the bond. So why we need to stretch, bend, or distort the bond? Reason is that the covalent molecules, in order to react, they must first break the bond. Right, so bond is either broken, then the bond is stretched. Right, so if you stretch a bond to an extent that it breaks, or you can bend the bond such that it breaks, or you may distort the bond such that it breaks. In order to break the bond, we need to have some energy. So this energy will do what? This energy will stretch the bond or bend the bond or distort the bond so that the bond gets broken. So this minimum amount of energy which is required for breaking the bond is called activation energy. Let's consider this diagram here. You can here see this on this axis we have energy. So energy is increasing on this axis, and we have reaction coordinate along the x-axis. So you can see here this is the reactant, right? So reactant, in order to convert into product, this must get some minimum of energy. This minimum of energy is called activation energy. So once a reactant gets this minimum amount of energy, it will form something called activated complex. So activated complex is another word for transition state. Right? The reactant must form a transition state first. So you know what the transition state is? An imaginary state of high energy in which the bonds are being broken and they're being formed. Right? So they are not actually broken and they are not actually formed. So this is some sort of imaginary state. So the reactants must have some minimum amount of energy, which is called activation energy. So once the reactant gets this minimum amount of energy, they form the activated complex or the transition state. And once the transition state is formed, so this complex will convert into the product. So in the reverse direction, you can say that in order for the product, right, you can see here the product has less energy. In order for the product to get converted into this reactant, this product must gain that much amount of activation energy. Right, so this is quite a huge amount of energy, right? So if the product gets this much amount of energy, this product will form the transition state and will get converted into the reactant, right? So this is why, because the energy is required in a huge amount, therefore the reverse of this reaction does not occur. And we say that product, since it has lower energy, the product is more stable, and the product does not prefer to go in the reverse direction, right? This diagram is also indicating that the relative energy difference between reactant and product, like this one, means the product has this delta H amount of energy lower than the reactant, right? So as a general rule, we all know that lower the energy, higher the stability. Since the product is lowering energy by amount of delta H, therefore we say that a product is stable by amount of this delta H energy. So this energy, this diagram which we are showing here, this diagram is called the activation energy diagram, or it's also known as the energy profile diagram, right? So this activation energy diagram or the energy profile diagram provides following information. This will give you the sequence of events. Alright, so in the diagram, suppose we go in the previous side, let's say reactant. So reactant is first forming the transition state and it's converted into product. So nothing else is happening. So in case if you have a reaction in which what happens that we get some intermediate as well. So the transition state is always indicated by this hump, right, by this peak. But whenever we have some transition state, if we have some reactive intermediate, then in that case, in addition to the transition state, we will also get some intermediate like this one. So for example, if reaction like that one and the reaction involves formation of a reactive intermediate, right, so intermediate will appear in the form of a valley, right? So this is our reactant and this is our product, right? And you can see here that this hump which is being formed, this hump is indicating the transition state, and this valley which is indicating as a loop, right? This is a valley, this is indicating the reactive intermediate, and this is again a transition state, and this is the product, right? So in this way, the transition state, the activation energy diagram will help you understand what is the sequence of events. So in which sequence we get the transition state, in which sequence we get the intermediate, etc. Right? Then the energy profile diagram provides information about the reaction coordinate. The reaction coordinate represents how the energy changes take place during a chemical reaction. How much energy is absorbed, how much energy is emitted, right? So it's the relative energy of the reactant and products. So this all information is provided by the reaction coordinate. Next we have activation energy. So as we see that in the previous slide, that the activation energy appears in the form of hump, right? So activation energy is the minimum energy which is required to start a reaction, right? So this is the information that's provided by the energy profile diagram, and the energy profile diagram also indicates you the presence of transition state or the reaction intermediate, right? So as mentioned earlier, the activated complex is also known as transition state. The activated complex is an imaginary species, right? So that's not a real one, right? So since this is an imaginary species, you cannot isolate it, right? You cannot have it isolated in your lab, and you cannot store it in some vessel, etc. You cannot store it in some bottle. Next we have intermediate. So intermediate is a short-lived species. A short-lived species means it is formed for a very, very, very small time, but it is formed it's an actual species. High energy, right? Just like transition state, it has also high energy. It's a reactive molecule, right? It's generated in the chemical reaction, and it is quickly converted into a stable product, right? They cannot remain like that. Why? Because it's very highly reactive, right? So in some circumstances you can isolate the reactive intermediate. For example, by lowering the temperature, you can isolate reactive intermediate. So the difference between a transition state and a reactive intermediate or reaction intermediate is that a transition state is an imaginary state, while reaction intermediate is a real species, right? So you can never ever detect or isolate a transition state, but you can detect and you can isolate the reaction intermediates. So all carbocations, carbanions, the free radicals, these are all examples of intermediates, right? So now let's consider about the types of organic reaction mechanisms, right? So you know that each functional group has their own reactivity. Some functional groups will undergo addition, some will undergo substitution, some will undergo condensation reactions, right? So depending on the functional group, each functional group has its own reactivity, right? So we have discussed about different type of reactions in the previous lecture. So all of those reactions which we have discussed in the previous lecture, all of them can be classified into three basic types on the basis of their mechanism, right? So what are these basic types? So all of these reactions can be classified either as polar mechanisms, free radical mechanisms, or pericyclic mechanisms. So we shall discuss briefly each of them. But before we are going to discuss each of them, let's consider about a term which is very important, that's kinetic stability and the thermodynamic stability. Right? So kinetics means, as you have studied in the physical chemistry, the kinetics is related to the rate of reaction. Right? So we say that if a reaction is taking place faster, we say that's kinetically favorable, and if a reaction is taking place slowly, we say this is not favored by kinetics, right? The kinetics is related to the reactivity. If a substrate is more reactive, the reaction will occur faster, right? And the product which is formed at a slow rate, we say this is not favored kinetically because it's not reactive, right? So kinetics is related to reactivity. So the product which is formed faster is said to be kinetically favored, or we say this is kinetically stable product. So reactive species which react faster to form product, they will be kinetically stable, right? So one thing is important here, that if a thing is kinetically stable, it doesn't mean that it may be thermodynamically stable or not. So what do we mean by thermodynamic stability? Thermodynamics has to deal with the energy. It's not to deal with the reactivity. So thermodynamics is related to the stability. Right? So you know that in order for a thing to be stable, so Gibbs free energy should be lower, enthalpy should be lower, right? So if a product has a lower energy, means it will be less reactive, so that will be more stable. Right? So reactions that are preferred thermodynamically are spontaneous, and once the product is formed, then you have to give energy in order to reverse the reaction. Right? So kinetics deals with reactivity. So a thing which is more reactive will be formed at a faster rate, and a thing that is formed at a faster rate is kinetically stable product or is kinetically favored. Right? While thermodynamics has to deal with stability. Right? So if a product has a lower energy, we say it is thermodynamically favored and is thermodynamically stable. Right? So if a product that is kinetically stable, it may also be thermodynamically unstable. Right? If a product is kinetically stable, it may also be thermodynamically stable, or it can also be thermodynamically unstable, right? So the kinetic stability and thermodynamic stability are two different concepts, right? If a thing is kinetically stable, it may or may not be thermodynamically stable or not. So kinetics, always remember, kinetics has to be related with the rate of formation of the product, while thermodynamics deal with energetics, right? If a product is kinetically favored, means formed at a faster rate, but if that product is not thermodynamically stable, then the product will rearrange itself to form a thermodynamically favored product. Right? If a product is not thermodynamically stable, but it is kinetically stable, so always remember that this product will prefer to undergo rearrangement in order to form a thermodynamically favored product, right? Let's consider about the mechanisms. So as mentioned in the previous slide, the mechanisms are of three types: the polar reaction mechanism, the free radical mechanisms, and the pericyclic mechanisms. Polar mechanisms. Majority of the organic reactions occur by polar mechanism. Right, so it's a polar mechanism. Polar mechanism means the reactions that involve heterolytic cleavage. Right? So what type of reactions involve a heterolytic cleavage? For that, consider a bond. Right, so we are considering a bond between A and B. Right? Here is a bond between an atom A and atom B. Right? So suppose that this bond, each bond has 2 electrons. So if this bond breaks in such a way that B atom gets both of the electrons and A atom gets none, right? So in that case, you know that A, say it has lost both of electrons, so A will be positively charged, it will form a carbocation, and the B will form a negatively charged ion, right? So this bond breakage has resulted in unequal distribution of electrons. So we are getting a cation and we are getting an anion, right? So such type of cleavage in which the bond is broken in such a way that the two atoms get unequal distribution of electrons. One of the atom get both electrons and other atom gets none. So such type of cleavage is called heterolytic cleavage. Right? So this example, this is a heterolytic cleavage. Conversely, consider I'm just copying it and pasting it right. So consider another situation. So in that case, suppose that bond is being cleaved in such a way that bond is being broken in such a way that both atoms get equal number of electrons. So A is getting one electron and B is getting also one electron, right? So suppose right, so the single electrons is shown as a single dot. So let me magnify it for you. Right? So in this type of cleavage, the both atoms, after bond breaking, they are getting equal number of electrons. So such type of cleavage in which the atoms get equal number of electrons, this is called homolytic cleavage. So homolytic cleavage always results in formation of free radicals, while heterolytic cleavage always results in formation of cation and anion. So here, in polar mechanisms, the cleavage is heterolytic. So what result is that this mechanisms always result in formation of ionic intermediates, right? So whenever in any mechanism you are getting some carbocation or carbanion, you must be sure that this mechanism is a polar mechanism. So how can we distinguish a bond? How can we distinguish a mechanism to be a polar mechanism? Right? Certain features can help us. For example, in polar mechanisms, we can never break carbon-carbon or carbon-hydrogen bond. Right? In a polar mechanism, we never break non-polar bonds. So, the carbon-carbon bond is non-polar and carbon-hydrogen bonds are non-polar, right? So in polar mechanisms, we never break carbon-carbon or carbon-hydrogen bond. However, the bond between multiple carbon-carbon bonds, such as carbon-carbon double bond or carbon-carbon triple bond, such bonds are broken, right? Also, we can break a carbon-hydrogen bond which is activated by some functional group, right? So if a carbon-hydrogen bond is alpha to a carbonyl, then this carbon-hydrogen bond is polarized. So if a CH bond is polarized, it can be broken. But if a CH bond is highly non-polar, then in that case, polar mechanism does not involve breakage of the bond. So another indication is the presence of ions. So whenever you see that there are some ions either in the reactants or in the products, or the ions are being formed as an intermediate, right? So you can simply say the reaction is polar mechanism. Similarly, if in any mechanism you see H positive ion, right? So H positive ion is a very common ion that is involved in organic reactions. So whenever you see H positive ion, you can see that this reaction is a polar mechanism. Right? So all acid-base reactions belong to this polar mechanism category. Also, the polar mechanisms involve formation of a transition state which is polar. Also, they may result in formation of a reaction intermediate which are polar. Right? So since there is formation of a transition state or reaction intermediate which is polar, and that polar transition states and intermediates are stabilized by polar solvents, so that's why if any reaction is favored by a polar solvent, if any reaction is favored by a polar solvent, you should know that this mechanism should be a polar mechanism. Right? So I briefly described about polar mechanism. What's a polar mechanism? Polar mechanism involves formation of ions, or they may involve the use of ions as reactants, or we may also get some ions as a product. The next type of mechanism is the free radical mechanism. Right? So free radical mechanism are also known as the radical mechanisms. So these mechanisms involve homolytic cleavage. So in the previous slide, I showed you about the homolytic cleavage. So homolytic cleavage is a cleavage in which the two atoms undergo cleavage in such a way that both atoms get one electron each, right? So the free radical reaction mechanisms involve the typical chain initiation step, chain propagation, and chain termination. We also know that the reaction inhibitors, they slow down the chain reaction, right? And the radical disproportionation is competing radical reactions, right? So what are reaction inhibitors? Reaction inhibitors are the species which can just capture the free radical. So any species which, if it can capture a free radical, it will stop the radical reaction. And what's the disproportionation reaction? Disproportionation reaction is a reaction in which same species is oxidized as well as reduced. For example, here consider this is an example. So here we are taking two species, right? So in disproportionation reaction, we'll see that one of the species is oxidized. Why we are saying oxidized? Because it's losing a proton here. Right? The loss of proton will result in formation of a carbon-carbon double bond. Right? So just let's remove this type of sign. Right? So species in which species is reduced and oxidized as well. So this species is losing a proton here. Right? So after losing a proton, it will form a double bond. The loss of proton is called oxidation. So here it's becoming oxidized. The other species here, it is gaining the proton, right? It's being reduced. You can also imagine that this radical, it can abstract a hydrogen from this molecule. So if it can abstract a hydrogen from this molecule, so this will become a double bond and it will become a reduced species, right? It will get reduced and it will get oxidized. So both of these species can be oxidized and can be reduced, right? So if a species can be oxidized as well as reduced simultaneously, such a reaction is called disproportionation reaction, right? So free radical reactions, they are indicated by homolytic cleavage. So any reaction that involves homolytic cleavage, you should know that the mechanism will be a free radical mechanism, and the indication is that any reaction that involves the chain initiation step, chain propagation step, chain termination step, so this reaction will always be, the mechanism will always be the radical mechanism. Also, the disproportionation reaction and the inhibitors, they are characteristic of a radical mechanism, right? So radical reactions involve homolytic cleavage, right? So since radicals are not affected by polarity, right? The free radicals are not affected by polarity, so free radical reactions work well under non-polar conditions as well, right? So if a reaction is working well under non-polar conditions and the cleavage is homolytic, you can say for sure that the mechanism is a free radical mechanism, right? Another important thing is that the free radical mechanisms are very fast, right? The free radical reactions are fast. And what's the driving force for that? The driving force for these reactions is that the radical which is unpaired, it wants to become paired up, it wants to become a neutral species. So in attempt to become a neutral species, these free radicals, they react fastly so that they get paired up and become neutral species. Another important, you should know that free radical reactions are kinetically favored because they occur at a faster reaction rate, so these reactions are kinetically favored. So far we have discussed about the polar mechanisms. Polar mechanisms also called ionic mechanisms, and we have also seen about the reaction mechanism that involve the radical as intermediates, right? So when we are getting carbocation or carbanion as intermediates, we say their mechanism is polar or mechanism is ionic, and when we are getting the free radicals as reaction intermediate, we say their mechanism is a free radical mechanism, right? So there are certain reactions that proceed via concerted mechanism, right? Concerted is a mechanism in which multiple steps occur simultaneously, right? Multiple steps occur at the same time, right? So that's a concerted reaction. And the important thing about pericyclic reaction is that they occur simultaneously, means they are concerted reactions, and they always proceed by a cyclic transition state. So if you have a reaction mechanism which is concerted, means multiple steps are occurring simultaneously, and the reaction proceeds via cyclic transition state, such type of mechanism is called pericyclic mechanisms. These reactions require heat or light for initiation, right? So pericyclic reaction, you will never observe any electrophile, any nucleophile, you will never observe any electrofuge or nucleofuge, you will never observe any free radical, right? So pericyclic reactions, they involve lighter heat for initiation. They are completely stereospecific. So it's completely stereospecific means you get only one product from the reactant. So depending on your reactant, if you're using a single stereoisomer, that single stereoisomer will only result in formation of a single stereoisomer as a product. So they are stereospecific reaction, they are concerted reaction, and they always proceed via cyclic transition state. Right. So pericyclic reaction involves formation of a cyclic transition state. Right. The reactions are concerted, and the orbitals involved in the pericyclic reaction, they overlap in a cyclic transition state, right? So the transition state is formed when the orbitals, they overlap in a cyclic manner, right? So such type of reactions are called pericyclic reactions, right? So I hope you have understood about the three types of reaction mechanisms. So in general, if any mechanism results in formation of ions, such as carbocation, carbanion, you can say that this is a polar mechanism. If any reaction involves formation of a free radical, then the reaction will be considered as free radical mechanism. While if any reaction is a concerted stereospecific reaction and involves formation of a cyclic transition state, then in that case we say that mechanism is a pericyclic mechanism. Thank you for your attention.